Today what we've got coming off then? I'm Andrew Cripps, I'm the ADM supervisor. It's my job to look after the ADM department and the ADM technicians that work within it. ADM stands for Additive Digital Manufacturing. That encompasses all of the industrial 3D printing technologies that we use here at Williams. Right now we are stood in the SLA machine room. We have a bunch of SLA printers that are working tirelessly to make parts for the team. The machine takes a photopolymer resin and uses a UV light to cure it into three-dimensional shapes. The machines run 24 hours, 7 days a week, producing about 500 parts a week on average. We have various different types of 3D printer with different applications, mainly because of different materials for driving different performance gains. For the SLA technology that you can see around us, it starts with a build plate at the top of the resin surface. The UV laser will turn on and cure that first 0.1 of a mil layer of the component. The build plate dips down, fresh resin is applied, and then another laser turns on and you get another layer. That repeats until you get your final product. After the product is printed, it goes on to post-processing where we remove excess materials, and then it goes on to be used where it's supposed to go.
My name is Julie Godwin. I am a materials engineer specialising in additive manufacturing. So what that means is quite a range of things.
Julie will support the ADM department as a materials engineer. If there's a new technology, a new material that we want to explore, she'll help validate that material with testing in the materials lab.
Advising designers as well on material choice and material applications, helping set up new machines or new materials and validating that essentially the product that we're expecting to have is the product that we have received and the product that we can produce. And that information will then go back to Andy and his team and also to the designers upstairs who are designing the parts that will be made in that material or on that machine.
Then we can have evidence to go to the engineering team. This is really interesting. Okay. Do you think you can use it?
You just grip the specimen in each end and then it will pull apart and then you basically get a result of how strong it is, amongst many other things. There are parts on the car that are made from these machines.
From a turnkey solution, you could print a part overnight, have it at the next race, and it's on the car.
The great advantage of SLA is it is really fast and you do get a really good turnaround. Bracketry, covers, something to fill a gap in another component. That's a really good one for SLA because it's just really quick turnaround time.
The main customer is the wind tunnel, but we also make jigs, fixtures and tooling for composites, which are enablers for them to laminate the composite components, and then we also make direct parts that go straight to the race car. So this is an example of an assembly of SLA parts for the wind tunnel model, of all of these individual 3D printed components that make up this assembly. Part of the component has been 3D printed with these little tubes, and the tubes go through here into the bottom of the aerodynamic surfaces. This is the only way that we can make the tube in one part is to use 3D printing, and that is part of the pressure tappings we call that. It's just how they get their data. There will be a pressure difference between the top and bottom surfaces, like an aeroplane, and they can use that to read those pressure differences to understand what that means.
There is a predominant usage within the wind tunnel for SLA because of that quick turnaround, because of the iterations and the material consumption that we have.
They might want to concentrate on a specific part that they want to optimize. So we'll print lots of versions of the same part and then they'll bolt it into this assembly and test it in the tunnel. So it just gives them so much more freedom to do small batch runs of components to look for the best version.
It's also very repeatable, so if it's something that needs to break or something that needs to be replaced every single race, things like that are really good for that kind of application.
Williams invested in this technology back in the late 80s, early 90s, and ever since then it's grown from rapid prototyping for making functional prototypes all the way up to now end-use products that we print and go straight onto the car. Traditionally, before it became mainstream and relied upon, they were hand sanding and crafting those components. So as soon as this became available, that sped up the development curve for the wind tunnel dramatically, which wouldn't have been possible with people manually forming those shapes out of tooling block or whatever it may be.
We can outsource this sort of thing, but the lead time goes up, the cost goes up, so that development iteration goes down significantly and the cost goes up significantly as well. So it's a lot less favourable, I suppose, if you have it outsourced.
And these are literally just support towers that take off.
It would massively reduce the cadence of development for performance from the wind tunnel. That is the driving force of the upgrades, of the initial outline of the car. So without this technology, we can't keep bringing upgrades to the car.
We wouldn't get the iterations, we wouldn't get the development, we wouldn't be able to test new designs, new theories, new concepts. So that development side of things would completely go out the window. So we'd probably get a car scrap, but we'd be P19, P20 every single weekend.
We're in a really good position right now with the industry of additive manufacturing. It's now much more understood. It's becoming a relied upon manufacturing method. So we can see it in social media, you can see it everywhere.
It's a really big and growing industry, so it's kind of become a lot more than it initially ever was.
You've got complete geometric freedom to make whatever you want. So essentially, if you can imagine it, you